tennis player in a wheelchair on a tennis court strikes a ball as it meets their racket. Figure 3.1, hitting a tennis ball is difficult enough when it is traveling at high speeds in a relatively straight line. However, most motion is in curved, rather than straight-line paths. Tennis players must account for the arc of the ball and the impact of its spin, while they also predict how it will bounce and plan the location of their shot. Motion along a curved path is 2- or 3-dimensional motion and can be described in a similar fashion to one-dimensional motion. Credit Edwin Martinez/Flickr. Chapter Outline 3.1 Kinematics in 2 Dimensions, an Introduction. 3.2 Vector Addition and Subtraction, Graphical Methods. 3.3 Vector Addition and Subtraction, Analytical Methods. 3.4 Projectile Motion. 3.5 Addition of Velocities. The arc of a basketball, the orbit of a satellite, a bicycle rounding a curve, a swimmer diving into a pool, blood gushing out of a wound, and a puppy chasing its tail are but a few examples of motions along curved paths. In fact, most motions in nature follow curved paths rather than straight lines. Motion along a curved path on a flat surface or a plane, such as that of a ball on a pool table or a skater on an ice rink, is 2-dimensional and thus described by 2-dimensional kinematics. Motion not confined to a plane, such as a car following a winding mountain road, is described by 3-dimensional kinematics. Both 2- and 3-dimensional kinematics are simple extensions of the 1-dimensional kinematics developed for straight-line motion in the previous chapter. This simple extension will allow us to apply physics to many more situations, and it will also yield unexpected insights about nature. Learning objectives. By the end of this section, you will be able to observe that motion in 2 dimensions consists of horizontal and vertical components. Understand the independence of horizontal and vertical vectors in 2-dimensional motion. A busy traffic intersection in New York showing vehicles moving on the road. Figure 3.2 Walkers and drivers in a city like New York are rarely able to travel in straight lines to reach their destinations. Instead, they must follow roads and sidewalks, making 2-dimensional, zigzagged paths. Credit Margaret W. Carruthers. 2-dimensional motion, walking in a city. Suppose you want to walk from one point to another in a city with uniform square blocks, as pictured in Figure 3.3. An XY graph with origin at 0, 0, with x-axis labeled 9 blocks east and y-axis labeled 5 blocks north. Starting point at the origin and destination at point 9 on the x-axis and point 5 on the y-axis. Figure 3.3, a pedestrian walks a 2-dimensional path between 2 points in a city. In this scene, all blocks are square and are the same size. The straight-line path that a helicopter might fly is blocked to you as a pedestrian, and so you are forced to take a 2-dimensional path, such as the one shown. You walk 14 blocks in all, 9 east followed by 5 north. What is the straight-line distance? An old adage states that the shortest distance between 2 points is a straight line. The 2 legs of the trip and the straight-line path form a right triangle, and so the Pythagorean theorem, a2 plus b2 equals c2, can be used to find the straight-line distance. A right-angled triangle with base, labeled a height labeled b, and hypotenuse labeled c is shown. Using Pythagorean theorem, c is calculated as square root of a squared plus b squared. Figure 3.4, the Pythagorean theorem relates the length of the legs of a right triangle, labeled a, and b, with the hypotenuse, labeled c. The relationship is given by a2 plus letter 1d44f2 equals c2. This can be rewritten, solving for c. c equals a2 plus letter 1d44f2 square. The hypotenuse of the triangle is the straight line path, and so in this case its length in units of city blocks is 9 blocks, 2 plus 5 blocks, 2 square equals 10.3 blocks. Considerably shorter than the 14 blocks you walked. Note that we are using 3 significant figures in the answer. Although it appears that 9 and 5 have only one significant digit, they are discrete numbers. In this case, 9 blocks is the same as 9 or 9 blocks. We have decided to use 3 significant figures in the answer in order to show the result more precisely. An XY graph with origin at 0, 0, with x-axis labeled 9 blocks east and y-axis labeled 5 blocks north. A diagonal vector arrow joining starting point at point 0 on x-axis and destination at point 5 on y-axis with its direction northeast is shown. A helicopter is flying along the diagonal vector arrow with helicopter path of 10.3 blocks. The angle formed by diagonal vector arrow and the x-axis is equal to 29.1 degrees. Figure 3.5, the straight line path followed by a helicopter between the 2 points is shorter than the 14 blocks walked by the pedestrian. All blocks are square and the same size. The fact that the straight line distance, 10.3 blocks, in figure 3.5 is less than the total distance walked, 14 blocks, is one example of a general characteristic of vectors. Recall that vectors are quantities that have both magnitude and direction. As for one-dimensional kinematics, we use arrows to represent vectors. The length of the arrow is proportional to the vector's magnitude. The arrow's length is indicated by hash marks in figure 3.3 and figure 3.5. The arrow points in the same direction as the vector. For two-dimensional motion, the path of an object can be represented with 3 vectors. One vector shows the straight line path between the initial and final points of the motion, one vector shows the horizontal component of the motion, and one vector shows the vertical component of the motion. The horizontal and vertical components of the motion add together to give the straight line path. For example, observe the 3 vectors in figure 3.5. The first represents a 9-block displacement east. The second represents a 5-block displacement north. These vectors are added to give the third vector, with a 10.3-block total displacement. The third vector is the straight line path between the 2 points. Note that in this example, the vectors that we are adding are perpendicular to each other and thus form a right triangle. This means that we can use the Pythagorean theorem to calculate the magnitude of the total displacement. Note that we cannot use the Pythagorean theorem to add vectors that are not perpendicular. We will develop techniques for adding vectors having any direction, not just those perpendicular to one another, in vector addition and subtraction, graphical methods and vector addition and subtraction, analytical methods. The independence of perpendicular motions. The person taking the path shown in figure 3.5 walks east and then north 2 perpendicular directions. How far they walk east is only affected by their motion eastward. Similarly, how far they walk north is only affected by their motion northward. Independence of motion. The horizontal and vertical components of two-dimensional motion are independent of each other. Any motion in the horizontal direction does not affect motion in the vertical direction, and vice versa. This is true in a simple scenario like that of walking in one direction first, followed by another. It is also true of more complicated motion involving movement in 2 directions at once. For example, let's compare the motions of 2 baseballs. One baseball is dropped from rest. At the same instant, another is thrown horizontally from the same height and follows a curved path. A stroboscope has captured the positions of the balls at fixed time intervals as they fall. 2 identical balls, one red and another blue, are falling. 5 positions of the balls during fall are shown. The horizontal velocity vectors for blue ball towards right are of same magnitude for all the positions. The vertical velocity vectors shown downwards for red ball are increasing with each position. Figure 3.6, this shows the motions of 2 identical balls. One falls from rest, the other has an initial horizontal velocity. Each subsequent position is an equal time interval. Arrows represent horizontal and vertical velocities at each position. The ball on the right has an initial horizontal velocity, while the ball on the left has no horizontal velocity. Despite the difference in horizontal velocities, the vertical velocities and positions are identical for both balls. This shows that the vertical and horizontal motions are independent. It is remarkable that for each flash of the strobe, the vertical positions of the 2 balls are the same. This similarity implies that the vertical motion is independent of whether or not the ball is moving horizontally. Assuming no air resistance, the vertical motion of a falling object is influenced by gravity only, and not by any horizontal forces. Careful examination of the ball thrown horizontally shows that it travels the same horizontal distance between flashes. This is due to the fact that there are no additional forces on the ball in the horizontal direction after it is thrown. This result means that the horizontal velocity is constant, and affected neither by vertical motion nor by gravity, which is vertical. Note that this case is true only for ideal conditions. In the real world, air resistance will affect the speed of the balls in both directions. The two-dimensional curved path of the horizontally thrown ball is composed of two independent one-dimensional motions, horizontal and vertical. The key to analyzing such motion, called projectile motion, is to break it into motions along perpendicular directions. Resolving two-dimensional motion into perpendicular components is possible because the components are independent. We shall see how to resolve vectors in vector addition and subtraction, graphical methods, and vector addition and subtraction, analytical methods. We will find such techniques to be useful in many areas of physics. pH at explorations. Ladybug motion 2D. Learn about position, velocity, and acceleration vectors. Move the ladybug by setting the position, velocity, or acceleration and see how the vectors change. Choose linear, circular, or elliptical motion and record and playback the motion to analyze the behavior. Click to view content. By the end of this section, you will be able to understand the rules of vector addition, subtraction, and multiplication by scalars. Apply graphical methods of vector addition and subtraction to determine the displacement of moving objects. Some Hawaiian islands like Kauai, Oahu, Molokai, Lanai, Maui, Kaho'olawe, and Hawaii are shown. On the scale map of Hawaiian Islands, the path of a journey is shown moving from Hawaii to Molokai. The path of the journey is turning at different angles and finally reaching its destination. The displacement of the journey is shown with the help of a straight line connecting its starting point and the destination. Figure 3.7 displacement can be determined graphically using a scale map, such as this one of the Hawaiian Islands. A journey from Hawaii to Molokai has a number of legs or journey segments. These segments can be added graphically with a ruler to determine the total two-dimensional displacement of the journey. Credit: U.S. Geological Survey. Vectors in two dimensions. A vector is a quantity that has magnitude and direction. Displacement, velocity, acceleration, and force, for example, are all vectors. In one-dimensional or straight-line motion, the direction of a vector can be given simply by a plus or minus sign. In two dimensions 2D, however, we specify the direction of a vector relative to some reference frame, i.e., coordinate system, using an arrow having length proportional to the vector's magnitude and pointing in the direction of the vector. Figure 3.8 shows such a graphical representation of a vector, using as an example the total displacement for the person walking in a city considered in kinematics in two dimensions. An introduction. We shall use the notation that a boldface symbol, such as D, stands for a vector. Its magnitude is represented by the symbol in italics, D, and its direction by letter 1D703. Vectors in this text. In this text, we will represent a vector with a boldface variable. For example, we will represent the quantity force with the vector F, which has both magnitude and direction. The magnitude of the vector will be represented by a variable in italics, such as F, and the direction of the variable will be given by an angle, letter 1D703. A graph is shown. On the axes, the scale is set to 1 block is equal to 1 unit. A helicopter starts moving from the origin at an angle of 29.1 degrees above the x-axis. The current position of the helicopter is 10.3 blocks along its line of motion. The destination of the helicopter is the point which is 9 blocks in the positive x direction and 5 blocks in the positive y direction. The positive direction of the x-axis is east, and the positive direction of the y-axis is north. Figure 3.8, a person walks 9 blocks east and 5 blocks north. The displacement is 10.3 blocks at an angle 29.10. North of east. On a graph, a vector is shown. It is inclined at an angle theta equal to 29.1 degrees above the positive x-axis. A protractor is shown to the right of the x-axis to measure the angle. A ruler is also shown parallel to the vector to measure its length. The ruler shows that the length of the vector is 10.3 units. Figure 3.9, to describe the resultant vector for the person walking in a city, considered in Figure 3.8 graphically. draw an arrow to represent the total displacement vector d. Using a protractor, draw a line at an angle letter 1d703. Relative to the east-west axis, the length d of the arrow is proportional to the vector's magnitude and is measured along the line with a ruler. In this example, the magnitude d of the vector is 10.3 units, and the direction letter 1d703 is 29.10. North of east. Vector addition, head-to-tail method. The head-to-tail method is a graphical way to add vectors, described in figure 3.1 below and in the steps following. The tail of the vector is the starting point of the vector, and the head, or tip, of a vector is the final, pointed end of the arrow. In part A, a vector of magnitude of 9 units and making an angle of theta is equal to 0 degrees is drawn from the origin and along the positive direction of x-axis. In part B, a vector of magnitude of 9 units and making an angle of theta is equal to 0 degree is drawn from the origin and along the positive direction of x-axis. Then a vertical arrow from the head of the horizontal arrow is drawn. In part C, a vector d of magnitude 10.3 is drawn from the tail of the horizontal vector at an angle theta is equal to 29.1 degrees from the positive direction of x-axis. The head of the vector d meets the head of the vertical vector. A scale is shown parallel to the vector d to measure its length. Also, a protractor is shown to measure the inclination of the vector d. Figure 3.1 Head-to-tail method. The head-to-tail method of graphically adding vectors is illustrated for the two displacements of the person walking in a city considered in figure 3.8. A. Draw a vector representing the displacement to the east. B. Draw a vector representing the displacement to the north. The tail of this vector should originate from the head of the first, east-pointing vector. C. Draw a line from the tail of the east-pointing vector to the head of the north-pointing vector to form the sum or resultant vector d. The length of the arrow d is proportional to the vector's magnitude and is measured to be 10.3 units. Its direction, described as the angle with respect to the east, or horizontal axis, letter 1d703, is measured with a protractor to be 29.10. Step 1. Draw an arrow to represent the first vector, 9 blocks to the east, using a ruler and protractor. In part A, a vector of magnitude of 9 units, and making an angle theta is equal to 0 degree, is drawn from the origin and along the positive direction of x-axis. Figure 3.11. Step 2. Now draw an arrow to represent the second vector, 5 blocks to the north. Place the tail of the second vector at the head of the first vector. In part B, a vector of magnitude of 9 units and making an angle theta is equal to 0 degree is drawn from the origin and along the positive direction of x-axis. Then a vertical vector from the head of the horizontal vector is drawn. Figure 3.12. Step 3. If there are more than 2 vectors, continue this process for each vector to be added. Note that in our example, we have only 2 vectors, so we have finished placing arrows tip to tail. Step 4. Draw an arrow from the tail of the first vector to the head of the last vector. This is the resultant, or the sum, of the other vectors. In part C, a vector d of magnitude 10.3 is drawn from the tail of the horizontal vector at an angle theta is equal to 29.1 degrees from the positive direction of the x-axis. The head of the vector d meets the head of the vertical vector. A scale is shown parallel to the vector d to measure its length. Also, a protractor is shown to measure the inclination of the vector d. Figure 3.13. Step 5. To get the magnitude of the resultant, measure its length with a ruler. Note that in most calculations, we will use the Pythagorean theorem to determine this length. Step 6. To get the direction of the resultant, measure the angle it makes with the reference frame using a protractor. Note that in most calculations, we will use trigonometric relationships to determine this angle. The graphical addition of vectors is limited in accuracy only by the precision with which the drawings can be made and the precision of the measuring tools. It is valid for any number of vectors. Example 3.1. Adding vectors graphically using the head-to-tail method. A woman takes a walk. Use the graphical technique for adding vectors to find the total displacement of a person who walks the following 3 paths, displacements, on a flat field. First, she walks 25 m in a direction 49.0, north of east. Then she walks 23 m heading 15.0, north of east. Finally, she turns and walks 32 m in a direction 68.0 degrees south of east. Strategy: represent each displacement vector graphically with an arrow, labeling the first A, the second B, and the third C, making the lengths proportional to the distance and the directions as specified relative to an east-west line. The head-to-tail method outlined above will give a way to determine the magnitude and direction of the resultant displacement, denoted R. Solution: 1. Draw the 3 displacement vectors. On the graph, a vector of magnitude 23 meters and inclined above the x-axis at an angle theta b equal to 15 degrees is shown. This vector is labeled as B. Figure 3.14. 2. Place the vector's head to tail, retaining both their initial magnitude and direction. In this figure, a vector A with a positive slope is drawn from the origin. Then from the head of the vector, another vector B with positive slope is drawn, and then another vector C with negative slope from the head of the vector B is drawn, which cuts the x-axis. Figure 3.15. 3. Draw the resultant vector. In this figure, a vector A with a positive slope is drawn from the origin. Then from the head of the vector, another vector B with positive slope is drawn, and then another vector C with negative slope from the head of the vector B is drawn, which cuts the x-axis. From the tail of the vector, a vector R of magnitude of 50.8 meters and with negative slope of 5.47 degrees is drawn. The head of this vector R meets the head of the vector C. The vector R is known as the resultant vector. Figure 3.16. 4. Use a ruler to measure the magnitude of R and a protractor to measure the direction of R. While the direction of the vector can be specified in many ways, the easiest way is to measure the angle between the vector and the nearest horizontal or vertical axis. Since the resultant vector is south of the eastward pointing axis, we flip the protractor upside down and measure the angle between the eastward axis and the vector. In this figure, a vector A with a positive slope is drawn from the origin. Then from the head of the vector, another vector B with positive slope is drawn, and then another vector C with negative slope from the head of the vector B is drawn, which cuts the x-axis. From the tail of the vector, a vector R of magnitude of 50.8 meters and with negative slope of 5.47 degrees is drawn. The head of this vector R meets the head of the vector C. The vector R is known as the resultant vector. A ruler is placed along the vector R to measure it. Also, there is a protractor to measure the angle. Figure 3.17. In this case, the total displacement R is seen to have a magnitude of 50.8 m and to lie in a direction 5.470 south of east. By using its magnitude and direction, this vector can be expressed as letter 1d445 equals 50, 8 m, and letter 1d703 equals 5, 47.0 south of east. Discussion: the head-to-tail graphical method of vector addition works for any number of vectors. It is also important to note that the resultant is independent of the order in which the vectors are added. Therefore, we could add the vectors in any order as illustrated in figure 3.18, and we will still get the same solution. In this figure, a vector C with a negative slope is drawn from the origin. Then from the head of the vector C, another vector A with positive slope is drawn, and then another vector B with negative slope from the head of the vector A is drawn. From the tail of the vector C, a vector R of magnitude of 50.8 meters and with negative slope of 5.47 degrees is drawn. The head of this vector R meets the head of the vector B. The vector R is known as the resultant vector. Figure 3.18. Here, we see that when the same vectors are added in a different order, the result is the same. This characteristic is true in every case and is an important characteristic of vectors. Vector addition is commutative. Vectors can be added in any order. Letter 1d400 plus letter 1d401 equals letter 1d401 plus letter 1d400. 3.1. This is true for the addition of ordinary numbers as well. You get the same result whether you add 2 plus 3 or 3 plus 2. For example, vector subtraction. Vector subtraction is a straightforward extension of vector addition. To define subtraction, say we want to subtract b from a. Writ letter 1d400, letter 1d401. We must first define what we mean by subtraction. The negative of a vector b is defined to be b. That is, graphically the negative of any vector has the same magnitude but the opposite direction, as shown in figure 3.19. In other words, b has the same length as b, but points in the opposite direction. Essentially, we just flip the vector so it points in the opposite direction. Two vectors are shown. One of the vectors is labeled as vector in northeast direction. The other vector is of the same magnitude and is in the opposite direction to that of vector b. This vector is denoted as negative b. Figure 3.19, the negative of a vector is just another vector of the same magnitude but pointing in the opposite direction. So b is the negative of b. It has the same length but opposite direction. The subtraction of vector b from vector a is then simply defined to be the addition of b to a. Note that vector subtraction is the addition of a negative vector. The order of subtraction does not affect the results. ab equals a plus b. 3.2. This is analogous to the subtraction of scalars, where, for example, 2 equals 5 plus 2. Again, the result is independent of the order in which the subtraction is made. When vectors are subtracted graphically, the techniques outlined above are used, as the following example illustrates. Example 3.2. Subtracting vectors graphically, a woman sailing a boat. A woman sailing a boat at night is following directions to a dock. The instructions read to first sail 27.5 m in a direction 66.0, north of east from her current location, and then travel 30 m in a direction 112.0, north of east or 22.0, west of north. If the woman makes a mistake and travels in the opposite direction for the second leg of the trip, where will she end up? Compare this location with the location of the dock. A vector of magnitude 27.5 meters is shown. It is inclined to the horizontal at an angle of 66 degrees. Another vector of magnitude 30.0 meters is shown. It is inclined to the horizontal at an angle of 112 degrees. Figure 3.2. Strategy. We can represent the first leg of the trip with a vector a and the second leg of the trip with a vector b. The dock is located at a location a plus b. If the woman mistakenly travels in the opposite direction for the second leg of the journey, she will travel a distance b, 30 m, in the direction 180.0 112.0 equals 68.0. South of east, we represent this as b. As shown below, the vector b has the same magnitude as b, but is in the opposite direction. Thus, she will end up at a location letter 1d400 plus letter 1d401, or letter 1d400, letter 1d401. A vector labeled negative b is inclined at an angle of 68 degrees below a horizontal line. A dotted line in the reverse direction, inclined at 112 degrees above the horizontal line, is also shown. Figure 3.21. We will perform vector addition to compare the location of the dock, a plus b, with the location at which the woman mistakenly arrives, a plus b. Solution. 1. To determine the location at which the woman arrives by accident, draw vectors a and b. 2. Place the vectors head to tail. 3. Draw the resultant vector r. 4. Use a ruler and protractor to measure the magnitude and direction of r. Vectors a and negative b are connected in head-to-tail method. Vector a is inclined with horizontal with positive slope, and vector negative b with a negative slope. The resultant of these two vectors is shown as a vector r from tail of a to the head of negative b. The length of the resultant is 23.0 meters and has a negative slope of 7.5 degrees. Figure 3.22. In this case, letter 1D445 equals 23, 0 m, and letter 1D703 equals 7, 5 0. South of east. 5. To determine the location of the dock, we repeat this method to add vectors A and B. We obtain the resultant vector R. A vector A inclined at 66 degrees with horizontal is shown. From the head of this vector, another vector B is started. Vector B is inclined at 112 degrees with the horizontal. Another vector labeled as R' from the tail of vector A to the head of vector B is drawn. The length of this vector is 52.9 meters, and its inclination with the horizontal is shown as 90.1 degrees. Vector R' is equal to the sum of vectors A and B. Figure 3.23. In this case, R equals 52.9 m, and letter 1D703 equals 90, 10. North of east. We can see that the woman will end up a significant distance from the dock if she travels in the opposite direction for the second leg of the trip. Discussion. Because subtraction of a vector is the same as addition of a vector with the opposite direction, the graphical method of subtracting vectors works the same as for addition. Multiplication of vectors and scalars. If we decided to walk 3 times as far on the first leg of the trip considered in the preceding example, then we would walk 3 times 27.5 m, or 82.5 m, in a direction 66.0. North of east. This is an example of multiplying a vector by a positive scalar. Notice that the magnitude changes, but the direction stays the same. If the scalar is negative, then multiplying a vector by it changes the vector's magnitude and gives the new vector the opposite direction. For example, if you multiply by 2, the magnitude doubles but the direction changes. We can summarize these rules in the following way. When vector A is multiplied by a scalar c, the magnitude of the vector becomes the absolute value of c. If c is positive, the direction of the vector does not change. If c is negative, the direction is reversed. In our case, letter 1D450 equals 3, and letter 1D434 equals 27, 5 m. Vectors are multiplied by scalars in many situations. Note that division is the inverse of multiplication. For example, dividing by 2 is the same as multiplying by the value 1, 2. The rules for multiplication of vectors by scalars are the same for division. Simply treat the divisor as a scalar between 0 and 1. Resolving a vector into components. In the examples above, we have been adding vectors to determine the resultant vector. In many cases, however, we will need to do the opposite. We will need to take a single vector and find what other vectors added together produce it. In most cases, this involves determining the perpendicular components of a single vector, for example, the x and y components, or the north-south and east-west components. For example, we may know that the total displacement of a person walking in a city is 10.3 blocks in a direction 29.0. North of east, and want to find out how many blocks east and north had to be walked. This method is called finding the components or parts of the displacement in the east and north directions, and it is the inverse of the process followed to find the total displacement. It is one example of finding the components of a vector. There are many applications in physics where this is a useful thing to do. We will see this soon in projectile motion, and much more when we cover forces in dynamics, Newton's laws of motion. Most of these involve finding components along perpendicular axes, such as north and east, so that right triangles are involved. The analytical techniques presented in vector addition and subtraction, analytical methods are ideal for finding vector components. pH at explorations. Maze game. Learn about position, velocity, and acceleration in the arena of pain. Use the green arrow to move the ball. Add more walls to the arena to make the game more difficult. Try to make a goal as fast as you can. Click to view content. Learning objectives. By the end of this section, you will be able to understand the rules of vector addition and subtraction using analytical methods, Apply analytical methods to determine vertical and horizontal component vectors. Apply analytical methods to determine the magnitude and direction of a resultant vector. Analytical methods of vector addition and subtraction employ geometry and simple trigonometry rather than the ruler and protractor of graphical methods. Part of the graphical technique is retained because vectors are still represented by arrows for easy visualization. However, analytical methods are more concise, accurate, and precise than graphical methods, which are limited by the accuracy with which a drawing can be made. Analytical methods are limited only by the accuracy and precision with which physical quantities are known. Resolving a vector into perpendicular components. Analytical techniques and right triangles go hand in hand in physics because, among other things, motions along perpendicular directions are independent. We very often need to separate a vector into perpendicular components. For example, given a vector like A. In Figure 3.24, we may wish to find which two perpendicular vectors, x and letter 1D400, letter 1D466, add to produce it. In the given figure, a dotted vector, a sub x, is drawn from the origin along the x-axis. From the head of the vector, a sub x, another vector, a sub y, is drawn in the upward direction. Their resultant vector A is drawn from the tail of the vector, a sub x, to the head of the vector, a sub y, at an angle theta from the x-axis. On the graph, a vector A, inclined at an angle theta with x-axis, is shown. Therefore, vector A is the sum of the vectors a sub x and a sub y. Figure 3.24, the vector A, with its tail at the origin of an x, y coordinate system, is shown together with its x and y components, x and letter 1D400, letter 1D466. These vectors form a right triangle. The analytical relationships among these vectors are summarized below. X and letter 1D400, letter 1D466 are defined to be the components of A. Along the x and y axes, the three vectors A, x, and letter 1D400, letter 1D466 form a right triangle. X plus letter 1D400, letter 1D466 equals A. 3.3. Note that this relationship between vector components and the resultant vector holds only for vector quantities, which include both magnitude and direction. The relationship does not apply for the magnitudes alone. For example, if letter 1D400, letter 1D465 equals 3m, east, letter 1D400, letter 1D466 equals 4m, north, and letter 1D400 equals 5m, northeast, then it is true that the vectors x plus letter 1D400, letter 1D466 equals A. However, it is not true that the sum of the magnitudes of the vectors is also equal. That is, 3m plus 4m not equal to 5m. 3.4. Thus, letter 1D434, letter 1D465 plus letter 1D434, letter 1D466 not equal to letter 1D434. 3.5. If the vector A is known, then its magnitude A, its length, and its angle letter 1D703, its direction are known to find x, and letter 1D434, letter 1D466. Its x and y components, we use the following relationships for a right triangle. Letter 1D434, letter 1D465 equals letter 1D434 C, O, S, letter 1D703. 3.6. And letter 1D434, letter 1D466 equals letter 1D434, S, I, N, letter 1D703. 3.7. A dotted vector, a sub x, whose magnitude is equal to a cosine theta, is drawn from the origin along the x-axis. From the head of the vector, a sub x, another vector, a sub y whose magnitude is equal to a sine theta, is drawn in the upward direction. Their resultant vector A is drawn from the tail of the vector, a sub x, to the head of the vector ay at an angle theta from the x-axis. Therefore, vector A is the sum of the vectors a sub x and a sub y. Figure 3.25, the magnitudes of the vector components x and letter 1D400, letter 1D466 can be related to the resultant vector A and the angle letter 1D703 with trigonometric identities. Here we see that letter 1D434, letter 1D465 equals letter 1D434, C, O, S, letter 1D703. And letter 1D434, letter 1D466 equals letter 1D434, S, I, N, letter 1D703. Suppose, for example, that A is the vector representing the total displacement of the person walking in a city considered in kinematics in 2 dimensions. An introduction and vector addition and subtraction, graphical methods. In the given figure, a vector A of magnitude 10.3 blocks is inclined at an angle 29.1 degrees to the positive x-axis. The horizontal component, a sub-x of vector A, is equal to a cosine theta, which is equal to 10.3 blocks multiplied to cosine 29.1 degrees, which is equal to 9 blocks east. Also, the vertical component, a sub-y of vector A, is equal to a sin theta, is equal to 10.3 blocks multiplied to sine 29.1 degrees, which is equal to 5.0 blocks north. Figure 3.26, we can use the relationships letter 1D434, letter 1D465 equals letter 1D434, C, O, S, letter 1D703. And letter 1D434, letter 1D466 equals letter 1D434, S, I, N, letter 1D703. To determine the magnitude of the horizontal and vertical component vectors in this example. Then letter 1D434 equals 10, 3. Blocks and letter 1D703 equals 29, 10. So that letter 1D434, letter 1D465 equals letter 1D434, C, O, S, letter 1D703 equals 10, 3 blocks. Cos 29, 10 equals 9, 0 blocks. 3.8. Letter 1D434, letter 1D466 equals letter 1D434, SIN letter 1D703 equals 10, 3 blocks. Sin 29, 10 equals 5, 0 blocks. 3.9. Calculating a resultant vector. If the perpendicular components x and letter 1D400, letter 1D466 of a vector A are known, then A can also be found analytically to find the magnitude A and direction, letter 1D703, of a vector from its perpendicular components x and letter 1D400, letter 1D466. Relative to the x-axis, we use the following relationships. Letter 1D434 equals letter 1D434, letter 1D465, 2 plus letter 1D434, letter 1D466, 2 square. 3.1. Letter 1D703 equals tan minus 1, letter 1D434, letter 1D466, slash letter 1D434, letter 1D465. 3.11. Vector A is shown with its horizontal and vertical components a sub x and a sub y respectively. The magnitude of vector A is equal to the square root of a sub x squared plus a sub y squared. The angle theta of the vector A with the x-axis is equal to inverse tangent of a sub y over a sub x. Figure 3.27, the magnitude and direction of the resultant vector can be determined once the horizontal and vertical components x and letter 1D434, letter 1D466 have been determined. Note that the equation letter 1D434 equals letter 1D434 to x plus a to letter 1D466 square is just the Pythagorean theorem relating the legs of a right triangle to the length of the hypotenuse. For example, if x and letter 1D434, letter 1D466 are 9 and 5 blocks, respectively, then letter 1D434 equals 92 plus 52 square equals 10, 3. Blocks, again consistent with the example of the person walking in a city. Finally, the direction is tan. As before, determining vectors and vector components with analytical methods. Equations letter 1D434, letter 1D465 equals letter 1D434, C, O, S, letter 1D703. And letter 1D434, letter 1D466 equals letter 1D434, S, I, N, letter 1D703, are used to find the perpendicular components of a vector, that is, to go from A and letter 1D703 to x and letter 1D434, letter 1D466 Equations letter 1d434 equals letter 1d434 to x plus a to letter 1d466 square. And tan are used to find a vector from its perpendicular components, that is, to go from x, and letter 1d434 letter 1d466 to a, and letter 1d703. Both processes are crucial to analytical methods of vector addition and subtraction. Adding vectors using analytical methods. To see how to add vectors using perpendicular components, consider figure 3.28, in which the vectors a and b are added to produce the resultant r. Two vectors a and b are shown. The tail of vector b is at the head of vector a, and the tail of the vector a is at origin. Both the vectors are in the first quadrant. The resultant r of these two vectors extending from the tail of vector a to the head of vector b is also shown. Figure 3.28 vectors a and b are two legs of a walk, and r is the resultant or total displacement. You can use analytical methods to determine the magnitude and direction of r. If a and b represent two legs of a walk, two displacements, then r is the total displacement. The person taking the walk ends up at the tip of r. There are many ways to arrive at the same point. In particular, the person could have walked first in the x direction and then in the y direction. Those paths are the x and y components of the resultant letter 1d411 letter 1d465 and letter 1d411 letter 1d466. If we know letter 1d411 letter 1d465 and letter 1d411 letter 1d466, we can find r and letter 1d703. Using the equations letter 1d434 equals letter 1d434 letter 1d465, 2 plus letter 1d434 letter 1d466, 2 square. And tan. When you use the analytical method of vector addition, you can determine the components or the magnitude and direction of a vector. Step 1. Identify the x and y axes that will be used in the problem. Then, find the components of each vector to be added along the chosen perpendicular axes. Use the equations letter 1d434 letter 1d465 equals letter 1d434 c o s letter 1d703 and letter 1d434 letter 1d466 equals letter 1d434 sin letter 1d703. To find the components, in figure 3.29, these components are x, letter 1d434 letter 1d466, letter 1d435 letter 1d465, and by the angles that vectors a and b make with the x-axis are letter 1d703a and letter 1d703b, respectively. Two vectors a and b are shown. The tail of the vector b is at the head of vector a, and the tail of the vector a is at origin. Both the vectors are in the first quadrant. The resultant r of these two vectors extending from the tail of vector a to the head of vector b is also shown. The horizontal and vertical components of the vectors a and b are shown with the help of dotted lines. The vectors labeled as a sub x and a sub y are the components of vector a, and b sub x and b sub y as the components of vector b. Figure 3.29 to add vectors a and b. First, determine the horizontal and vertical components of each vector. These are the dotted vectors x, letter 1d400 letter 1d466, letter 1d40 1 letter 1d465, and by, shown in the image. Step 2. Find the components of the resultant along each axis by adding the components of the individual vectors along that axis. That is, as shown in figure 3.3. Letter 1d445 letter 1d465 equals letter 1d434 letter 1d465 plus letter 1d435 letter 1d465. 3.12. And letter 1d445 letter 1d466 equals letter 1d434 letter 1d466 plus letter 1d435 letter 1d466. 3.13. Two vectors a and b are shown. The tail of vector b is at the head of vector a, and the tail of the vector a is at origin. Both the vectors are in the first quadrant. The resultant r of these two vectors extending from the tail of vector A to the head of vector B is also shown. The vectors A and B are resolved into the horizontal and vertical components shown as dotted lines parallel to x-axis and y-axis respectively. The horizontal components of vector A and vector B are labeled as a sub x and b sub x, and the horizontal component of the resultant r is labeled at r sub x and is equal to a sub x plus b sub x. The vertical components of vector A and vector B are labeled as a sub y and b sub y, and the vertical components of the resultant r is labeled as r sub y is equal to a sub y plus b sub y. Figure 3.3, the magnitude of the vectors x. And letter 1d40, 1 letter 1d465. Add to give the magnitude, letter 1d445, letter 1d465. Of the resultant vector in the horizontal direction. Similarly, the magnitudes of the vectors letter 1d400, letter 1d466. And by add to give the magnitude letter 1d445, letter 1d466. Of the resultant vector in the vertical direction. Components along the same axis, say the x-axis, are vectors along the same line and thus can be added to one another like ordinary numbers. The same is true for components along the y-axis. For example, a 9-block eastward walk could be taken in 2 legs, the first 3 blocks east and the second 6 blocks east, for a total of 9, because they are along the same direction. So resolving vectors into components along common axes makes it easier to add them. Now that the components of r are known, its magnitude and direction can be found. Step 3, to get the magnitude r of the resultant, use the Pythagorean theorem. Letter 1d445 equals letter 1d445 to x plus r2 letter 1d466 square. 3.14. Step 4, to get the direction of the resultant relative to the x-axis. Letter 1d703 equals tan minus 1, letter 1d445, letter 1d466, slash letter 1d445, letter 1d465. 3.15. The following example illustrates this technique for adding vectors using perpendicular components. Example 3.3. Adding vectors using analytical methods. Add the vector A to the vector B, shown in figure 3.31 using perpendicular components along the x and y axes. The x and y axes are along the east, west, and north, south directions, respectively. Vector A represents the first leg of a walk in which a person walks 53 m. In a direction 20 o. North of east, vector B represents the second leg, a displacement of 34 m. In a direction 63 o. North of east. 2 vectors A and B are shown. The tail of the vector A is at origin. Both the vectors are in the first quadrant. Vector A is of magnitude 53 units and is inclined at an angle of 20 degrees to the horizontal. From the head of the vector, another vector B of magnitude 34 units is drawn and is inclined at angle 63 degrees with the horizontal. The resultant of 2 vectors is drawn from the tail of the vector A to the head of the vector B. Figure 3.3, 1 vector A has magnitude 53 m and direction 20 o. North of the x-axis, vector B has magnitude 34 m and direction north of the x-axis. You can use analytical methods to determine the magnitude and direction of r. Strategy: the components of A and B along the x and y axes represent walking due east and due north to get to the same ending point. Once found, they are combined to produce the resultant. Solution: following the method outlined above, we first find the components of A and B along the x and y axes. Note that letter 1d434 equals 53, 0 m. Letter 1d703 equals 20, 0 o. Letter 1d435 equals 34, 0 m. And letter 1d703b equals 63, 0 o. We find the x components by using letter 1d434, letter 1d465 equals letter 1d434 c o s letter 1d703, which gives Letter 1D434 letter 1D465 equals letter 1D434 COS letter 1D703 A equals 53 0M cos 20 0 53 0M 0 940 equals 49 8M 3.16 and letter 1D435 letter 1D465 equals letter 1D435 COS letter 1D703 B equals 34 0M cos 63 0 34 0M 0 454 equals 15 4M 3.17 Similarly, the y components are found using letter 1D434 letter 1D466 equals letter 1D434 SIN letter 1D703 A. Letter 1D434 letter 1D466 equals letter 1D434 SIN letter 1D703 A equals 53 0M sin 20 0 53 0M 0 342 equals 18 1M 3.18 and letter 1D435 letter 1D466 equals letter 1D435 SIN letter 1D703 B equals 34 0M sin 63 0 34 0M 0 891 equals 30 3M 3.19 The x and y components of the resultant are thus letter 1D445 letter 1D465 equals letter 1D434 letter 1D465 plus letter 1D435 letter 1D465 equals 49 8M plus 15 4M equals 65 2M 3.2 and letter 1D445 letter 1D466 equals letter 1D434 letter 1D466 plus letter 1D435 letter 1D466 equals 18 1M plus 33M equals 48 4M 3.21 Now we can find the magnitude of the resultant by using the Pythagorean theorem. Letter 1D445 equals letter 1D445 to x plus r to letter 1D466 square equals 65 2 plus 48 4 2M square 3.22 so that letter 1D445 equals 81 2M 3.23 Finally, we find the direction of the resultant. Letter 1D703 equals tan minus 1, letter 1D445 letter 1D466 slash letter 1D445 letter 1D465 equals plus tan minus 1, 48, 4 slash 65, 2. 3.24. Thus, letter 1D703 equals tan minus 1, 0, 742 equals 36, 60. 3.25. The addition of two vectors A and B is shown. Vector A is of magnitude 53 units and is inclined at an angle of 20 degrees to the horizontal. Vector B is of magnitude 34 units and is inclined at angle 63 degrees to the horizontal. The components of vector A are shown as dotted vectors. A x is equal to 49.8 meter along x-axis, and a y is equal to 18.1 meter along y-axis. The components of vector B are also shown as dotted vectors bx is equal to 15.4 meter, and by is equal to 30.3 meter. The horizontal component of the resultant rx is equal to a x plus bx is equal to 65.2 meter. The vertical component of the resultant ry is equal to a y plus by is equal to 48.4 meter. The magnitude of the resultant of two vectors is 81.2 meters. The direction of the resultant r is in 36.6 degree from the vector A in anticlockwise direction. Figure 3.32, using analytical methods, we see that the magnitude of r is 81.2 m, and its direction is 36.60 north of east. Discussion. This example illustrates the addition of vectors using perpendicular components. Vector subtraction using perpendicular components is very similar. It is just the addition of a negative vector. Subtraction of vectors is accomplished by the addition of a negative vector. That is, letter 1D400 minus letter 1D401 identical to letter 1D400 plus letter 1D401. Thus, the method for the subtraction of vectors using perpendicular components is identical to that for addition. The components of B are the negatives of the components of B. The x and y components of the resultant letter 1D400 minus letter 1D401 equals r are thus letter 1D445 letter 1D465 equals letter 1D434 letter 1D465 plus letter 1D435 letter 1D465. 3.26 and letter 1D445 letter 1D466 equals letter 1D434 letter 1D466 plus letter 1D435 letter 1D466. 3.27 and the rest of the method outlined above is identical to that for addition. See figure 3.33. Analyzing vectors using perpendicular components is very useful in many areas of physics because perpendicular quantities are often independent of one another. The next module, projectile motion, is one of many in which using perpendicular components helps make the picture clear and simplifies the physics. In this figure, the subtraction of two vectors A and B is shown. A red-colored vector A is inclined at an angle theta A to the positive of x-axis. From the head of vector, a blue vector negative B is drawn. Vector B is in west of south direction. The resultant of the vector A and vector negative B is shown as a black vector R from the tail of vector A to the head of vector negative B. The resultant R is inclined to x-axis at an angle theta below the x-axis. The components of the vectors are also shown along the coordinate axes as dotted lines of their respective colors. Figure 3.33, the subtraction of the two vectors shown in figure 3.28. The components of B are the negatives of the components of B. The method of subtraction is the same as that for addition. pH at explorations. Vector addition. Learn how to add vectors. Drag vectors onto a graph, change their length and angle, and sum them together. The magnitude, angle, and components of each vector can be displayed in several formats. By the end of this section, you will be able to identify and explain the properties of a projectile, such as acceleration due to gravity, range, maximum height, and trajectory. Determine the location and velocity of a projectile at different points in its trajectory. Apply the principle of independence of motion to solve projectile motion problems. Projectile motion is the motion of an object thrown or projected into the air, subject to only the acceleration of gravity. The object is called a projectile, and its path is called its trajectory. The motion of falling objects, as covered in problem-solving basics for one-dimensional kinematics, is a simple one-dimensional type of projectile motion in which there is no horizontal movement. In this section, we consider two-dimensional projectile motion, such as that of a football or other object for which air resistance is negligible. The most important fact to remember here is that motions along perpendicular axes are independent and thus can be analyzed separately. This fact was discussed in kinematics in 2 dimensions. An introduction, where vertical and horizontal motions were seen to be independent. The key to analyzing two-dimensional projectile motion is to break it into 2 motions, one along the horizontal axis and the other along the vertical. This choice of axes is the most sensible because acceleration due to gravity is vertical. Thus, there will be no acceleration along the horizontal axis when air resistance is negligible. As is customary, we call the horizontal axis the x-axis and the vertical axis the y-axis. Figure 3.34 illustrates the notation for displacement, where s is defined to be the total displacement and x and y are its components along the horizontal and vertical axes, respectively. The magnitudes of these vectors are s, x, and y. Note that in the last section we used the notation a to represent a vector with components x and letter 1D400 letter 1D466. If we continued this format, we would call displacement s with components letter 1D42C letter 1D465 and letter 1D42C letter 1D466. However, to simplify the notation, we will simply represent the component vectors as x and y. Of course, to describe motion, we must deal with velocity and acceleration, as well as with displacement. We must find their components along the x and y axes, too. We will assume all forces except gravity, such as air resistance and friction, for example, are negligible. The components of acceleration are then very simple, ms2. Note that this definition assumes that the upwards direction is defined as the positive direction. If you arrange the coordinate system instead such that the downwards direction is positive, then acceleration due to gravity takes a positive value. Because gravity is vertical, letter 1d44 letter 1d465 equals 0. Both accelerations are constant, so the kinematic equations can be used. Review of kinematic equations, constant A. Letter 1d465 equals letter 1d4650 plus letter 1d463, letter 1d461. 3.28. Letter 1d463 equals letter 1d4630 plus letter 1d462. 3.29. Letter 1d463 equals letter 1d4630 plus letter 1d44 letter 1d461. 3.3. Letter 1d465 equals letter 1d4650 plus letter 1d4630, letter 1d461, plus 12 letter 1d44 letter 1d461 2. 3.31. Letter 1d463 2 equals letter 1d463 20 plus 2 letter 1d440, letter 1d465 minus letter 1d4650. 3.32. A soccer player is kicking a soccer ball. The ball travels in a projectile motion and reaches a point whose vertical distance is y and horizontal distance is x. The displacement between the kicking point and the final point is s. The angle made by this displacement vector with x-axis is theta. Figure 3.34, the total displacement s of a soccer ball at a point along its path, the vector s, has components x and y. Along the horizontal and vertical axes, its magnitude is s, and it makes an angle letter 1d703. With the horizontal. Given these assumptions, the following steps are then used to analyze projectile motion. Step 1. Resolve or break the motion into horizontal and vertical components along the x and y axes. These axes are perpendicular, so letter 1d434 letter 1d465 equals letter 1d434 c os letter 1d703. And letter 1d434 letter 1d466 equals letter 1d434 sin letter 1d703. Are used, the magnitude of the components of displacement s along these axes are x and y. The magnitudes of the components of the velocity v are letter 1d463 letter 1d465 equals letter 1d463 co s letter 1d703. And letter 1d463 letter 1d466 equals letter 1d463 sin theta, where v is the magnitude of the velocity and letter 1d703 is its direction, as shown in figure 3.35. Initial values are denoted with a subscript 0, as usual. Step 2. Treat the motion as two independent one-dimensional motions, one horizontal and the other vertical. The kinematic equations for horizontal and vertical motion take the following forms. Horizontal motion, letter 1d44 letter 1d465 equals 0. 3.33. Letter 1d465 equals letter 1d4650 plus letter 1d463 letter 1d465 letter 1d461. 3.34. Letter 1d463 letter 1d465 equals letter 1d463 0 letter 1d465 equals letter 1d463 letter 1d465 equals velocity is a constant. 3.35. Vertical motion, assuming positive, is up letter 1d440 letter 1d466 equals minus letter 1d454 equals minus 9. 80 m/s2. 3.36. Letter 1d466 equals letter 1d4660 plus 12, letter 1d4630 letter 1d466 plus letter 1d463 letter 1d466, letter 1d461. 3.37. Letter 1d463 letter 1d466 equals letter 1d463 0, letter 1d466 minus letter 1d454 letter 1d461. 3.38. Letter 1d466 equals letter 1d4660 plus letter 1d4630, letter 1d466 letter 1d461 minus 12 letter 1d454 letter 1d461 2. 3.39. V to letter 1d466 equals letter 1d463, 20 letter 1d466 minus 2 letter 1d454. Letter 1d466 minus letter 1d4660. 3.4. Step 3. Solve for the unknowns in the two separate motions, one horizontal and one vertical. Note that the only common variable between the motions is time t. The problem-solving procedures here are the same as for one-dimensional kinematics and are illustrated in the solved examples below. Step 4. Recombine the two motions to find the total displacement s and velocity v. Because the x and y motions are perpendicular, we determine these vectors by using the techniques outlined in the vector addition and subtraction. Analytical methods and employing letter 1d434 equals letter 1d434 to x plus a to letter 1d466 square. And letter 1d703 equals tan minus 1, letter 1d434 letter 1d466 slash letter 1d434 letter 1d465. In the following form, where letter 1d703 is the direction of the displacement s, and letter 1d703 letter 1d463 is the direction of the velocity v. Total displacement and velocity. 3.41. Letter 1d703 equals tan minus 1, letter 1d466 slash letter 1d465. 3.42. Letter 1d463 equals letter 1d463 to x plus v to letter 1d466 square. 3.43. Letter 1d703 letter 1d463 equals tan minus 1, letter 1d463 letter 1d466 slash letter 1d463 letter 1d465. 3.44. In part of the figure shows projectile motion of a ball with initial velocity of v0 at an angle of theta 0 with the horizontal x-axis. The horizontal component Vx and the vertical component Vy at various positions of ball in the projectile path is shown. In part B, only the horizontal velocity component V sub x is shown, whose magnitude is constant at various positions in the path. In part C, only vertical velocity component V sub y is shown. The vertical velocity component V sub y is upwards till it reaches the maximum point, and then its direction changes to downwards. In part D, resultant v of horizontal velocity component v sub x and downward vertical velocity component v sub y is found, which makes an angle theta with the horizontal x-axis. The direction of resultant velocity v is towards southeast. Figure 3.35a. We analyze two-dimensional projectile motion by breaking it into two independent one-dimensional motions along the vertical and horizontal axes. B. The horizontal motion is simple because letter 1d440 letter 1d465 equals 0. And letter 1d463 letter 1d465 is thus constant. C. The velocity in the vertical direction begins to decrease as the object rises. At its highest point, the vertical velocity is 0. As the object falls towards the Earth again, the vertical velocity increases again in magnitude but points in the opposite direction to the initial vertical velocity. D. The x and y motions are recombined to give the total velocity at any given point on the trajectory. Example 3.4. A fireworks projectile explodes high and away. During a fireworks display, a shell is shot into the air with an initial speed of 70 ms at an angle of 75°. Above the horizontal, as illustrated in figure 3.36, the fuse is timed to ignite the shell just as it reaches its highest point above the ground. A. Calculate the height at which the shell explodes. B. How much time passed between the launch of the shell and the explosion? C. What is the horizontal displacement of the shell when it explodes? Strategy. Because air resistance is negligible for the unexploded shell, the analysis method outlined above can be used. The motion can be broken into horizontal and vertical motions, in which letter 1d44 letter 1d465 equals 0. And letter 1d44 letter 1d466 equals letter 1d454. We can then define x0 and y0 to be 0 and solve for the desired quantities. Solution for A. By height, we mean the altitude or vertical position y. Above the starting point. The highest point in any trajectory, called the apex, is reached when letter 1d463 letter 1d466 equals 0. Since we know the initial and final velocities as well as the initial position, we use the following equation to find y. V to letter 1d466 equals letter 1d463, 20 letter 1d466 minus 2 letter 1d454. Letter 1d466 minus letter 1d466 0. 3.45. The XY graph shows the trajectory of fireworks shell. The initial velocity of the shell V0 is at angle theta 0 equal to 75 degrees with the horizontal x-axis. The fuse is set to explode the shell at the highest point of the trajectory, which is at a height h equal to 233 meters, and at a horizontal distance x equal to 125 meters from the origin. Figure 3.36, the trajectory of a fireworks shell. The fuse is set to explode the shell at the highest point in its trajectory, which is found to be at a height of 233 m and 125 m away horizontally. Because y0 and letter 1d463 letter 1d466 are both 0, the equation simplifies to 0 equals letter 1d463, 20 letter 1d466, minus 2 letter 1d454 letter 1d466. 3.46. Solving for y gives letter 1d466 equals letter 1d463, 20 letter 1d466 to g. 3.47. Now we must find v0y, the component of the initial velocity in the y direction. It is given by letter 1d4630, letter 1d466 equals letter 1d4630, sin letter 1d703, where v0y is the initial velocity of 70 ms and letter 1d7030 equals 75, 0, is the initial angle. Thus, letter 1d4630 letter 1d466 equals letter 1d4630 sin letter 1d7030 equals 70, 0 m/s. Sin 75 o equals 67, 6 ms. 3.48. And y is letter 1d466 equals 67, 6 m/s, 22 9, 80 ms2. 3.49. So that letter 1d466 equals 233 m. 3.5. Discussion for A. Note that because up is positive, the initial velocity is positive, as is the maximum height, but the acceleration due to gravity is negative. Note also that the maximum height depends only on the vertical component of the initial velocity, so that any projectile with a 67.6 ms initial vertical component of velocity will reach a maximum height of 233 m, neglecting air resistance. The numbers in this example are reasonable for large fireworks displays, the shells of which do reach such heights before exploding. In practice, air resistance is not completely negligible, and so the initial velocity would have to be somewhat larger than that given to reach the same height. Solution for B. As in many physics problems, there is more than one way to solve for the time to the highest point. In this case, the easiest method is to use letter 1d466 equals letter 1d4660 plus 12, letter 1d4630 letter 1d466 plus letter 1d463 letter 1d466, letter 1d461. Because y0 is 0, this equation reduces to simply letter 1d466 equals 12, letter 1d4630 letter 1d466 plus letter 1d463 letter 1d466, letter 1d461. 3.51. Note that the final vertical velocity, letter 1d463 letter 1d466, at the highest point is 0, thus, letter 1 d461 equals 2 letter 1 d466, letter 1 d4630y plus letter 1 d463 letter 1 d466 equals 233m, 67, 6m slash s, 6, 90s. 3.52. Discussion for B. This time is also reasonable for large fireworks. When you are able to see the launch of fireworks, you will notice several seconds pass before the shell explodes. Another way of finding the time is by using letter 1 d466 equals letter 1 d4660 plus letter 1 d4630, letter 1 d466 letter 1 d461, minus 12 letter 1 d454 letter 1 d461 2. And solving the quadratic equation for T. Solution for C. Because air resistance is negligible, letter 1 d440 letter 1 d465 equals 0. And the horizontal velocity is constant, as discussed above. The horizontal displacement is horizontal velocity multiplied by time as given by letter 1 d465 equals letter 1 d465 0 plus letter 1 d463 letter 1 d465 letter 1 d461, where x0 is equal to 0. Letter 1 d465 equals letter 1 d463 letter 1 d465 letter 1 d461. 3.53, where letter 1 d463 letter 1 d465 is the x component of the velocity, which is given by letter 1 d463 letter 1 d465 equals letter 1 d463 0 c o s letter 1 d7030. Now, letter 1 d463 letter 1 d465 equals letter 1 d463 0 c o s letter 1 d7030 equals 70, 0 m slash s, cos 75, 0 o equals 18, 1 ms. 3.54. The time t for both motions is the same, and so x is letter 1 d465 equals 18, 1 m slash s, 6, 90 s equals 125 m. 3.55. Discussion for C. The horizontal motion is a constant velocity in the absence of air resistance. The horizontal displacement found here could be useful in keeping the fireworks fragments from falling on spectators. Once the shell explodes, air resistance has a major effect, and many fragments will land directly below. In solving part A of the preceding example, the expression we found for y is valid for any projectile motion where air resistance is negligible. Call the maximum height letter 1 d466 equals letter 210e. Then, letter 210e equals letter 1 d463, 20 letter 1 d466 to g. 3.56. This equation defines the maximum height of a projectile and depends only on the vertical component of the initial velocity. Defining a coordinate system. It is important to set up a coordinate system when analyzing projectile motion. One part of defining the coordinate system is to define an origin for the x and y positions. Often, it is convenient to choose the initial position of the object as the origin such that letter 1 d4650 equals 0 and letter 1 d4660 equals 0. It is also important to define the positive and negative directions in the x and y directions. Typically, we define the positive vertical direction as upwards, and the positive horizontal direction is usually the direction of the object's motion. When this is the case, the vertical acceleration, letter 1 d440 letter 1 d466 equals letter 1 d454, takes a negative value since it is directed downwards towards the Earth. However, it is occasionally useful to define the coordinates differently. For example, if you are analyzing the motion of a ball thrown downwards from the top of a cliff, it may make sense to define the positive direction downwards since the motion of the ball is solely in the downwards direction. If this is the case, letter 1 d440 letter 1 d466 equals letter 1 d454 takes a positive value. Example 3.5. Calculating projectile motion, hot rock projectile. Kilauea in Hawaii is the world's most continuously active volcano. Very active volcanoes characteristically eject red-hot rocks and lava rather than smoke and ash. Suppose a large rock is ejected from the volcano with a speed of 25 ms and at an angle 35°. Above the horizontal, as shown in figure 3.37, the rock strikes the side of the volcano at an altitude 20 m lower than its starting point. A. Calculate the time it takes the rock to follow this path. B. What are the magnitude and direction of the rock's velocity at impact? The trajectory of a rock ejected from a volcano is shown. The initial velocity of rock V0 is equal to 25 meters per second, and it makes an angle of 35 degrees with the horizontal x-axis. The figure shows rock falling down a height of 20 meters below the volcano level. The velocity at this point is v, which makes an angle of theta with horizontal x-axis. The direction of v is southeast. Figure 3.37, the trajectory of a rock ejected from the Kilauea volcano. Strategy. Again, resolving this two-dimensional motion into two independent one-dimensional motions will allow us to solve for the desired quantities. The time a projectile is in the air is governed by its vertical motion alone. We will solve for t. First, while the rock is rising and falling vertically, the horizontal motion continues at a constant velocity. This example asks for the final velocity. Thus, the vertical and horizontal results will be recombined to obtain v. And letter 1D70, 3 letter 1D463. At the final time t. Determined in the first part of the example. Solution for A. While the rock is in the air, it rises and then falls to a final position 20 m lower than its starting altitude. We can find the time for this by using letter 1D466 equals letter 1D4660 plus letter 1D4630, letter 1D466, letter 1D461, minus 12, letter 1D454, letter 1D4612. 3.57. If we take the initial position y0 to be 0, then the final position is letter 1D466 equals minus 20, 0 m. Now the initial vertical velocity is the vertical component of the initial velocity, found from letter 1D4630, letter 1D466 equals letter 1D4630, sin letter 1D7030 equals 25 ms. Sin 35O equals 14.3 ms. Substituting known values yields minus 20, 0 m equals 14, 3 m slash s letter 1D461 minus 4, 90 m slash s2 letter 1D4612. 3.58. Rearranging terms gives a quadratic equation in t. 4.9 m slash s2 letter 1D4612 minus 14, 3 m slash s letter 1D461 minus 20, 0 m equals 0. 3.59. This expression is a quadratic equation of the form letter 1D44 letter 1D461, 2 plus letter 1D44f letter 1D461 plus letter 1D450 equals 0, where the constants are letter 1D44e equals 4, 90, letter 1D44f equals 14, 3, and letter 1D450 equals 20, 0. Its solutions are given by the quadratic formula. Letter 1D461 equals minus letter 1D44f plus or minus letter 1D44f, 2 minus 4 letter 1D44 letter 1D450 square 2 letter 1D44e. 3.6. This equation yields two solutions. Letter 1D461 equals 3, 96. And letter 1D461 equals 1, 0, 3. It is left as an exercise for the reader to verify these solutions. The time is s, or 1.03s. The negative value of time implies an event before the start of motion, and so we discard it. Thus, letter 1D461 equals 3, 96s. 3.61. Discussion for A. The time for projectile motion is completely determined by the vertical motion. So any projectile that has an initial vertical velocity of 14.3 ms and lands 20 m below its starting altitude will spend 3.96 s in the air. Solution for B. From the information now in hand, we can find the final horizontal and vertical velocities, letter 1D463, letter 1D465. and letter 1D463, letter 1D466, and combine them to find the total velocity v, and the angle letter 1D7030. It makes with the horizontal. Of course, letter 1D463, letter 1D465 is constant, so we can solve for it at any horizontal location. In this case, we chose the starting point since we know both the initial velocity and initial angle. Therefore, letter 1D463, letter 1D465 equals letter 1D463, 0 COS letter 1D703, 0 equals 25, 0 m/s, cos 30, 50 equals 20, 5 ms. 3.62. The final vertical velocity is given by the following equation. Letter 1D463, letter 1D466 equals letter 1D463, 0, letter 1D466 minus letter 1D454, letter 1D461. 3.63. Where V0y was found in part A to be 14.3 ms. Thus, letter 1D463, letter 1D466 equals 14, 3 m/s minus 9, 80 m/s2, 3, 96s. 3.64. So that letter 1D463, letter 1D466 equals minus 24, 5 ms. 3.65. To find the magnitude of the final velocity v, we combine its perpendicular components using the following equation. Letter 1D463 equals letter 1D463 plus v to letter 1D466 square equals 20. 5 m/s2 plus minus 24, 5 m/s2 square. 3.66, which gives letter 1D463 equals 31, 9 ms. 3.67, the direction letter 1D703, letter 1D463 is found from the equation. Letter 1D703, letter 1D463 equals tan minus 1, letter 1D463, letter 1D466 slash letter 1D463, letter 1D465. 3.68. So that letter 1D703, letter 1D463 equals tan minus 1 minus 24, 5 slash 20. 5 equals tan minus 1 minus 1, 19. 3.69. Thus, letter 1D703, letter 1D463 equals minus 50, 10. 3.7. Discussion for B. The negative angle means that the velocity is 50.10 below the horizontal. This result is consistent with the fact that the final vertical velocity is negative and hence downward, as you would expect because the final altitude is 20 m lower than the initial altitude. See Figure 3.37. One of the most important things illustrated by projectile motion is that vertical and horizontal motions are independent of each other. Galileo was the first person to fully comprehend this characteristic. He used it to predict the range of a projectile. On level ground, we define range to be the horizontal distance r traveled by a projectile. Galileo and many others were interested in the range of projectiles primarily for military purposes, such as aiming cannons. However, investigating the range of projectiles can shed light on other interesting phenomena, such as the orbits of satellites around the Earth. Let us consider projectile range further. Part of the figure shows 3 different trajectories of projectiles on level ground. In each case, the projectiles makes an angle of 45 degrees with the horizontal axis. The first projectile of initial velocity 30 meters per second travels a horizontal distance of r equal to 91.8 meters. The second projectile of initial velocity 40 meters per second travels a horizontal distance of r equal to 163 meters. The third projectile of initial velocity 50 meters per second travels a horizontal distance of r equal to 255 meters. Figure 3.38 trajectories of projectiles on level ground. A. The greater the initial speed v0, the greater the range for a given initial angle. B. The effect of initial angle letter 1D7030 on the range of a projectile with a given initial speed. Note that the range is the same for 15O and 75O, although the maximum heights of those paths are different. How does the initial velocity of a projectile affect its range? Obviously, the greater the initial speed v0, the greater the range, as shown in Figure 3:38a. The initial angle letter 1D7030 also has a dramatic effect on the range, as illustrated in Figure 3:38b. For a fixed initial speed, such as might be produced by a cannon, the maximum range is obtained with letter 1D7030 equals 4050. This is true only for conditions neglecting air resistance. If air resistance is considered, the maximum angle is approximately 3080. Interestingly, for every initial angle except 4050, there are two angles that give the same range. The sum of those angles is. The range also depends on the value of the acceleration of gravity g. The lunar astronaut Alan Shepard was able to drive a golf ball a great distance on the moon because gravity is weaker there. The range r of a projectile on level ground, for which air resistance is negligible, is given by letter 1D445 equals letter 1D463, 20 scintiletter 1D703, 0 letter 1D454. 3.71, where v0 is the initial speed and letter 1D7030 is the initial angle relative to the horizontal. The proof of this equation is left as an end-of-chapter problem. Hints are given, but it does fit the major features of projectile range as described. When we speak of the range of a projectile on level ground, we assume that r is very small compared with the circumference of the Earth. If, however, the range is large, the Earth curves away below the projectile and acceleration of gravity changes direction along the path. The range is larger than predicted by the range equation given above because the projectile has farther to fall than it would on level ground. See Figure 3.39. If the initial speed is great enough, the projectile goes into orbit. This possibility was recognized centuries before it could be accomplished. When an object is in orbit, the Earth curves away from underneath the object at the same rate as it falls. The object thus falls continuously, but never hits the surface. These and other aspects of orbital motion, such as the rotation of the Earth, will be covered analytically and in greater depth later in this text. Once again, we see that thinking about one topic, such as the range of a projectile, can lead us to others, such as the Earth orbits. In addition of velocities, we will examine the addition of velocities, which is another important aspect of two-dimensional kinematics and will also yield insights beyond the immediate topic. A figure of the Earth is shown, and on top of it, a very high tower is placed. A projectile satellite is launched from this very high tower with initial velocity of v0 in the horizontal direction. Several trajectories are shown with increasing range. A circular trajectory is shown indicating the satellite achieved its orbit and it is revolving around the Earth. Figure 3.39 hypothetical projectile to satellite. From this theoretical tower, a projectile is launched from a very high tower to avoid air resistance. With increasing initial speed, the range increases and becomes longer than it would be on level ground because the Earth curves away underneath its path. With a large enough initial speed, orbit is achieved. pH at explorations. Projectile motion. Blast a Buick out of a cannon. Learn about projectile motion by firing various objects. Set the angle, initial speed, and mass. Add air resistance. Make a game out of this simulation by trying to hit a target. By the end of this section, you will be able to apply principles of vector addition to determine relative velocity. Explain the significance of the observer in the measurement of velocity. Relative velocity. If a person rows a boat across a rapidly flowing river and tries to head directly for the other shore, the boat instead moves diagonally relative to the shore, as in Figure 3.4. The boat does not move in the direction in which it is pointed. The reason, of course, is that the river carries the boat downstream. Similarly, if a small airplane flies overhead in a strong crosswind, you can sometimes see that the plane is not moving in the direction in which it is pointed, as illustrated in Figure 3.41. The plane is moving straight ahead relative to the air, but the movement of the air mass relative to the ground carries it sideways. A boat is trying to cross a river. Due to the velocity of river, the path traveled by boat is diagonal. The velocity of boat v boat is in positive y direction. The velocity of river v river is in positive x direction. The resultant diagonal velocity v total, which makes an angle of theta with the horizontal x-axis, is towards northeast direction. Figure 3.4, a boat trying to head straight across a river will actually move diagonally relative to the shore as shown. Its total velocity, solid arrow, relative to the shore is the sum of its velocity relative to the river plus the velocity of the river relative to the shore. An airplane is trying to fly straight north with velocity v sub p due to wind velocity v sub w in southwest direction, making an angle theta with the horizontal axis. The plane's total velocity is 38.0 meters per second, oriented 20 degrees west of north. Figure 3.41, an airplane heading straight north is instead carried to the west and slowed down by wind. The plane does not move relative to the ground in the direction it points. Rather, it moves in the direction of its total velocity, solid arrow. In each of these situations, an object has a velocity relative to a medium, such as a river, and that medium has a velocity relative to an observer on solid ground. The velocity of the object relative to the observer is the sum of these velocity vectors, as indicated in Figure 3.4 and Figure 3.41. These situations are only two of many in which it is useful to add velocities. In this module, we first re-examine how to add velocities, and then consider certain aspects of what relative velocity means. How do we add velocities? Velocity is a vector. It has both magnitude and direction. The rules of vector addition discussed in vector addition and subtraction. Graphical methods and vector addition and subtraction. Analytical methods apply to the addition of velocities, just as they do for any other vectors. In one-dimensional motion, the addition of velocities is simple. They add like ordinary numbers. For example, if a field hockey player is moving at 5 ms straight toward the goal and drives the ball in the same direction with a velocity of 30 ms relative to her body, then the velocity of the ball is 35 ms. Relative to the stationary, profusely sweating goalkeeper standing in front of the goal. In two-dimensional motion, either graphical or analytical techniques can be used to add velocities. We will concentrate on analytical techniques. The following equations give the relationships between the magnitude and direction of velocity, v, and letter 1d703, and its components, letter 1d463, letter 1d465, and letter 1d463, letter 1d466, along the x and y axes of an appropriately chosen coordinate system. Letter 1d463, letter 1d465 equals letter 1d463, C, O, S letter 1d703. 3.72. Letter 1d463, letter 1d466 equals letter 1d463, S, I, N letter 1d703. 3.73. Letter 1d463 equals letter 1d463 to x plus v to letter 1d466 square. 3.74. Letter 1d703 equals tan minus 1, letter 1d463, letter 1d466, slash letter 1d463, letter 1d465. 3.75. The figure shows components of velocity v in horizontal x-axis, vx, and in vertical y-axis, vy. The angle between the velocity vector v and the horizontal axis is theta. Figure 3.42, the velocity v of an object traveling at an angle letter 1d703 to the horizontal axis is the sum of component vectors letter 1d4 letter 1d465 and letter 1d4 letter 1d466. These equations are valid for any vectors and are adapted specifically for velocity. The first two equations are used to find the components of a velocity when its magnitude and direction are known. The last two are used to find the magnitude and direction of velocity when its components are known. Take-home experiment, relative velocity of a boat. Fill a bathtub half full of water. Take a toy boat or some other object that floats in water. Unplug the drain so water starts to drain. Try pushing the boat from one side of the tub to the other and perpendicular to the flow of water. Which way do you need to push the boat so that it ends up immediately opposite? Compare the directions of the flow of water, heading of the boat, and actual velocity of the boat. Example 3.6. Adding velocities, a boat on a river. A boat is trying to cross a river. Due to the velocity of the river, the path traveled by the boat is diagonal. The velocity of the boat, v-boat, is equal to 0.75 meters per second and is in positive y direction. The velocity of the river, v-river, is equal to 1.2 meters per second and is in positive x direction. The resultant diagonal velocity v-total, which makes an angle of theta with the horizontal x-axis, is towards northeast direction. Figure 3.43. A boat attempts to travel straight across a river at a speed 0.75 ms. The current in the river, however, flows at a speed of 1.2 ms to the right. Refer to figure 3.43, which shows a boat trying to go straight across the river. Let us calculate the magnitude and direction of the boat's velocity relative to an observer on the shore, letter 1d42f tot. The velocity of the boat, letter 1d42f boat, is 0.75 ms in the y. Direction relative to the river and the velocity of the river, letter 1d42f river, is 1.2 ms to the right. Strategy. We start by choosing a coordinate system with its x-axis parallel to the velocity of the river, as shown in figure 3.43. Because the boat is directed straight toward the other shore, its velocity relative to the water is parallel to the y-axis and perpendicular to the velocity of the river. Thus, we can add the two velocities by using the equations letter 1d463 tot equals letter 1d463 plus v2 letter 1d466 square, and letter 1d703 equals tan minus 1, letter 1d463 letter 1d466 slash letter 1d463 letter 1d465. Directly. Solution. The magnitude of the total velocity is letter 1d463 tot equals letter 1d463 plus v2 letter 1d466 square. 3.76. Where letter 1d463 letter 1d465 equals letter 1d463 river equals 1.20 ms. 3.77. And letter 1d463 letter 1d466 equals letter 1d463 boat equals 0.750 ms. 3.78. Thus, letter 1d463 tot equals 1.20 ms 2 plus 0.750 m slash s2 square. 3.79. Yielding. Letter 1d463 tot equals 1.42 ms. 3.8. The direction of the total velocity, letter 1d703, is given by letter 1d703 equals tan minus 1, letter 1d463 letter 1d466 slash letter 1d463 letter 1d465 equals tan minus 1, 0, 750 slash 1, 20. 3.81. This equation gives letter 1d703 equals 32, 0, 0. 3.82. Discussion. Both the magnitude v and the direction, letter 1d703, of the total velocity are consistent with figure 3.43. Note that because the velocity of the river is large compared with the velocity of the boat, it is swept rapidly downstream. This result is evidenced by the small angle, only 30-0. The total velocity has relative to the riverbank. Example 3.7. Calculating velocity. Wind velocity causes an airplane to drift. Calculate the wind velocity for the situation shown in figure 3.44. The plane is known to be moving at 45 ms due north relative to the air mass, while its velocity relative to the ground, its total velocity, is 38 ms in a direction 20 west of north. An airplane is trying to fly north with velocity Vp equal to 45 meters per second at angle of 110 degrees. But due to wind velocity Vw in southwest direction, making an angle theta with the horizontal axis, it reaches a position in northwest direction with resultant velocity V total equal to 38 meters per second, and the direction is 20 degrees west of north. Figure 3.44, an airplane is known to be heading north at 45 ms, though its velocity relative to the ground is 38 ms at an angle west of north. What is the speed and direction of the wind? Strategy. In this problem, somewhat different from the previous example, we know the total velocity letter 1d42 tot, and that it is the sum of two other velocities, letter 1d42 fw. The wind and letter 1d42 fp. The plane relative to the air mass, the quantity letter 1d42 fp, is known, and we are asked to find letter 1d42 fw. None of the velocities are perpendicular, but it is possible to find their components along a common set of perpendicular axes. If we can find the components of letter 1d42 fw, then we can combine them to solve for its magnitude and direction. As shown in figure 3.44, we choose a coordinate system with its x-axis due east and its y-axis due north, parallel to letter 1d42 fp. You may wish to look back at the discussion of the addition of vectors using perpendicular components in vector addition and subtraction. Analytical methods. Solution. Because letter 1d42 f tot is the vector sum of the letter 1d42 fw and letter 1d42 fp. Its x and y components are the sums of the x and y components of the wind and plane velocities. Note that the plane only has vertical component of velocity, so letter 1d463p letter 1d465 equals 0. And that is letter 1d463 tot letter 1d465 equals letter 1d463w letter 1d465. 3.83. And letter 1d463 tot letter 1d466 equals letter 1d463w letter 1d466 plus letter 1d463p. 3.84. We can use the first of these two equations to find letter 1d463w letter 1d465. Letter 1d463w letter 1d465 equals letter 1d463 tot letter 1d465 equals letter 1d463 totcos 110.0. 3.85. Because letter 1d463 tot equals 38.0 ms and cos 110.0 equals 0, 342. We have letter 1d463w letter 1d465 equals 38.0 m/s 0, 342 equals 13 ms. 3.86. The minus sign indicates motion west, which is consistent with the diagram. Now, to find letter 1d463w letter 1d466. We note that letter 1d463 tot letter 1d466 equals letter 1d463w letter 1d466 plus letter 1d463p. 3.87. Here letter 1d463 tot letter 1d466 equals letter 1d463 totson 110.0. Thus, letter 1d463w letter 1d466 equals 38.0 m/s 0, 940 minus 45, 0 m/s equals minus 9, 29 ms. 3.88. This minus sign indicates motion south, which is consistent with the diagram. Now that the perpendicular components of the wind velocity, letter 1d463w letter 1d465, and letter 1d463w letter 1d466 are known, we can find the magnitude and direction of letter 1d42 fw. First, the magnitude is letter 1d463w equals letter 1d463 to w letter 1d465 plus letter 1d463 to w letter 1d466 square minus 13. 0 m/s2 plus minus 9, 29 m/s2 square. 3.89. So that letter 1d463w equals 16, 0 ms. 3.9. The direction is letter 1d703 equals tan minus 1, letter 1d463w letter 1d466 slash letter 1d463w letter 1d465 equals tan minus 1 minus 9, 29 slash minus 13, 0. 3.91. Giving letter 1d703 equals 35, 60. 3.92. Discussion. The wind's speed and direction are consistent with the significant effect the wind has on the total velocity of the plane, as seen in Figure 3.44. Because the plane is fighting a strong combination of crosswind and headwind, it ends up with a total velocity significantly less than its velocity relative to the air mass, as well as heading in a different direction. Note that in both of the last two examples, we were able to make the mathematics easier by choosing a coordinate system with one axis parallel to one of the velocities. We will repeatedly find that choosing an appropriate coordinate system makes problem solving easier. For example, in projectile motion, we always use a coordinate system with one axis parallel to gravity. Relative velocities and classical relativity. When adding velocities, we have been careful to specify that the velocity is relative to some reference frame. These velocities are called relative velocities. For example, the velocity of an airplane relative to an air mass is different from its velocity relative to the ground. Both are quite different from the velocity of an airplane relative to its passengers, which should be close to zero. Relative velocities are one aspect of relativity, which is defined to be the study of how different observers moving relative to each other measure the same phenomenon. Nearly everyone has heard of relativity and immediately associates it with Albert Einstein, 1879–1955, the greatest physicist of the 20th century. Einstein revolutionized our view of nature with his modern theory of relativity, which we shall study in later chapters. The relative velocities in this section are actually aspects of classical relativity, first discussed correctly by Galileo and Isaac Newton. Classical relativity is limited to situations where speeds are less than about 1% of the speed of light. That is, less than 3,000 km/s. Most things we encounter in daily life move slower than this speed. Let us consider an example of what two different observers see in a situation analyzed long ago by Galileo. Suppose a sailor at the top of a mast on a moving ship drops their binoculars. Where will it hit the deck? Will it hit at the base of the mast, or will it hit behind the mast because the ship is moving forward? The answer is that if air resistance is negligible, the binoculars will hit at the base of the mast at a point directly below its point of release. Now let us consider what two different observers see when the binoculars drop. One observer is on the ship and the other on shore. The binoculars have no horizontal velocity relative to the observer on the ship, and so he sees them fall straight down the mast. See Figure 3.45. To the observer on shore, the binoculars and the ship have the same horizontal velocity, so both move the same distance forward while the binoculars are falling. This observer sees the curved path shown in Figure 3.45. Although the paths look different to the different observers, each sees the same result. The binoculars hit at the base of the mast and not behind it. To get the correct description, it is crucial to correctly specify the velocities relative to the observer. A person is observing a moving ship from the shore. Another person is on top of ship's mast. The person in the ship drops binoculars and sees it dropping straight. The person on the shore sees the binoculars taking a curved trajectory. Figure 3.45 Classical relativity. The same motion is viewed by two different observers. An observer on the moving ship sees the binoculars dropped from the top of its mast fall straight down. An observer on shore sees the binoculars take the curved path, moving forward with the ship. Both observers see the binoculars strike the deck at the base of the mast. The initial horizontal velocity is different relative to the two observers. The ship is shown, moving rather fast to emphasize the effect. Example 3.8. Calculating relative velocity. An airline passenger drops a coin. An airline passenger drops a coin while the plane is moving at 260 ms. What is the velocity of the coin when it strikes the floor 1.5 m below its point of release? A. Measured relative to the plane. B. Measured relative to the earth. A person standing on ground is observing an airplane. Inside the airplane, a woman is sitting on seat. The airplane is moving in the right direction. The woman drops the coin, which is vertically downwards for her, but the person on ground sees the coin moving horizontally towards right. Figure 3.46, the motion of a coin dropped inside an airplane as viewed by two different observers. A. An observer in the plane sees the coin fall straight down. B. An observer on the ground sees the coin move almost horizontally. Strategy. Both problems can be solved with the techniques for falling objects and projectiles. In part A, the initial velocity of the coin is 0 relative to the plane, so the motion is that of a falling object one-dimensional. In part B, the initial velocity is 260 ms horizontal relative to the Earth and gravity is vertical, so this motion is a projectile motion. In both parts, it is best to use a coordinate system with vertical and horizontal axes. Solution for A. Using the given information, we note that the initial velocity and position are 0, and the final position is 1.5 m. The final velocity can be found using the equation. Letter 1d463 letter 1d4662 equals letter 1d4630. Letter 1d466 2 minus 2 letter 1d454. Letter 1d466 minus letter 1d4660. 3.93. Substituting known values into the equation, we get letter 1d463 letter 1d4662 equals 0 2 minus 2 9, 80 m slash s2 minus 1, 50 m minus 0 m equals 29, 4 m2 slash s2. 3.94. Yielding. Letter 1d463 letter 1d466 equals minus 5, 42 ms. 3.95. We know that the square root of 29.4 has two roots, 5.42 and minus 5.42. We choose the negative root because we know that the velocity is directed downwards, and we have defined the positive direction to be upwards. There is no initial horizontal velocity relative to the plane and no horizontal acceleration, and so the motion is straight down relative to the plane. Solution for B. Because the initial vertical velocity is 0 relative to the ground, and vertical motion is independent of horizontal motion, the final vertical velocity for the coin relative to the ground is letter 1d463 letter 1d466 equals minus 5, 42 m slash s. The same as found in part A. In contrast to part A, there now is a horizontal component of the velocity. However, since there is no horizontal acceleration, the initial and final horizontal velocities are the same, and letter 1d463 letter 1d465 equals 260 ms. The x and y components of velocity can be combined to find the magnitude of the final velocity. Letter 1d463 equals letter 1d463 letter 1d465, 2 plus letter 1d463 letter 1d466 2 square. 3.96. Thus, letter 1d463 equals 260 m slash s2 plus minus 5, 42 m slash s2 square. 3.97. Yielding. Letter 1d463 equals 260, 0.6 ms. 3.98. The direction is given by letter 1d703 equals tan minus 1, letter 1d463 letter 1d466 slash letter 1d463 letter 1d465 equals tan minus 1 minus 5, 42 slash 260. 3.99. So that letter 1d703 equals tan minus 1 minus 0, 0.208 equals minus 1, 19.0. 3.1. Discussion. In part A, the final velocity relative to the plane is the same as it would be if the coin were dropped from rest on the Earth and fell 1.5 m. This result fits our experience. Objects in a plane fall the same way when the plane is flying horizontally as when it is at rest on the ground. This result is also true in moving cars. In part B, an observer on the ground sees a much different motion for the coin. The plane is moving so fast horizontally to begin with that its final velocity is barely greater than the initial velocity. Once again, we see that in two dimensions, vectors do not add like ordinary numbers. The final velocity v in part B is not 265.42 ms. Rather, it is 260.06 ms. The velocity's magnitude had to be calculated to 5 digits to see any difference from that of the airplane. The motions as seen by different observers, one in the plane and one on the ground, in this example are analogous to those discussed for the binoculars dropped from the mast of a moving ship, except that the velocity of the plane is much larger, so that the two observers see very different paths. See Figure 3.46. In addition, both observers see the coin fall 1.5 m vertically, but the one on the ground also sees it move forward 144 m. This calculation is left for the reader. Thus, one observer sees a vertical path, the other a nearly horizontal path. Making connections, relativity and Einstein. Because Einstein was able to clearly define how measurements are made, some involve light, and because the speed of light is the same for all observers, the outcomes are spectacularly unexpected. Time varies with observer, energy is stored as increased mass, and more surprises await. pH at explorations. Motion in 2D. Try the motion in 2D simulation to learn about position, velocity, and acceleration vectors. Move the ball with the mouse, or let the simulation move the ball in 4 types of motion: 2 types of linear, simple harmonic, circle. Click to view content,